Okay. So what does it mean when we put a little number up there above another number? What's that? It is the power, so we call it. What does it mean? It times itself however many times. You remember our discussion about that phrasing? Okay. So, not that, I'll be mad at you if you say that or anything like that, or I'll judge you a little, I guess, but it's not times itself 3 times, right? Because if you multiply something by itself, there it is 2 of them. Multiply by itself once, and there's 2 of them. So, I would say, like 3 factors of this. So, however you say it, I think we all get what it means, what we need to do. So, up here we have 3 to the third, right? 3 times 3 times 3, that's 27. 5 to the third down here, 125. Okay, which property is being used in number 27? Yes, associative. How did you remember that? You just remember it, so you know, oh come on, you gotta have something. There's 2 of them. Okay, and did you just eliminate commutative then? Just remember them. What about this speaks to you and says this is the associative property? Okay. Okay. Any others you had?
Oh, because the parentheses move.
Because the parentheses move, the numbers don't move, the parentheses move. Okay? All right. Well, yes, that is the associative property. Remember, at least the way that I remember it is that the root word is associate. And to associate just means to work together, right? That's what Caleb said, or to just like communicate to each other. So like -6 and 1 are communicating with each other, and then 7 comes in afterwards. That would be the same as 1 and 7 communicating, adding, finding the sum of those 2, and then -6 coming in after that. So that they're just, it's dependent on who's associating with each other first. So either way, it doesn't matter. So we're going to evaluate this, should have written expression, evaluate this expression when x is equal to -3. So how do we do that? I know it seems obvious, but I want somebody still to say.
Substitute -3 for x.
Very well said. Yeah, substitute -3 for x. -3 plus a -5 plus 5. And here's the associative property at work. Whether we add these together first or add these together first, it's not going to make a difference, right? This is convenient because -5 plus 5, 0. And we'll add -3 to 0 and get -3. Right. 13 minus -5. What's it mean if you subtract a negative? So you're just adding the positive. Subtracting a negative is the same as adding a positive. So 13 plus 5 is 18. Again, we're subtracting a negative, so we'll add a positive. And now what do we need? Yes, Cameron?
I know the answer.
Oh, how'd you get the answer? Wow, I'm going to take that away from you. I'm going to smash it, even though it's mine.
Okay.
I'm gonna smash it. Don't rely on your calculator. If you rely on your calculator, don't. All right. What do we need to do, Bridger?
The 3.4. Oh, 3 over 4.
3 over 4. Yeah. Different. But how did you get it?
Well, I added 1/4 to 1/2.
Okay.
I just know that you could do 4.
Okay. You didn't use your calculator like Cameron did?
I didn't.
Which you just know.
Yeah,
Okay. Want something a little more, oh, Nathan. Okay, that's the important thing. Yeah, the common denominator. Lots of people knew that. Okay. What is the common denominator? It's 4. Okay. This already has it. So this is the only one that needs to be taken to that common denominator. So how does that go? How do we do that? 2 fourths. So we just know it. All right. Or we, if we want to be real technical, multiply by 2 over 2. Right. 1/2 is pretty simple. Whatever it is, it needs to simplify down to 1/2. So to do that with fourths, you do 2 fourths. So 2 fourths plus 1/4 is 3 fourths. Okay. And this guy down here, what's that look like? What are we going to do to evaluate the expression? Caleb?
Substitute the numbers of the letters into the numbers.
Other way around, I think. The numbers into the letters? Yeah, whatever. That's what we do, right? So 3.6 minus 6.6. Group those together and then subtract. What is this?
Absolute value.
Absolute value. What does the absolute value mean? It's got a definition.
How far it is from 0.
How far it is from 0. You can't stop Maria. She's just got the answers spilling out. 3.6 minus 6.6. Cameron?
-3.
Good.
I didn't use the calculator.
Oh, I'm proud of you now. I'm proud of you. So, -3. Okay, what's the absolute value of 11? 11. It's 11 away from 0. So minus 11, -14. Right. Questions from any of that? No, I hear no's. Oh, I see no's. I see this. That means no to me. Any questions from the homework in general? Any other problems that you have trouble with? Okay. Then let's pass in our homework. Sweet, then that pink slip to come in. Alright, so today, it's a goal of mine to try and help you, well, to inform you before we get started what it is we're going to be talking about. I know to kind of cram it in there, it's a little small, and you might not be able to read it from your seats, but if you're curious, it's up there. So we'll start with, it's just like the official section on order of operations, so we'll drive that home. And notice, what I write here is, we're going to apply our order of operations. Why do I say our order of operations? Caleb?
Which is the way that we learned it.
Right. It's the way we're going to learn it, and so I want you to go out into the world aware of the fact that there is no reason why that is the order of operations. There is no the order of operations. But the one we're going to use is widely accepted. I think more widely accepted than the one where multiplication always comes first. But there's no reason why even multiplication has become before addition other than we say that it does. But that's what we're going to do. So that's where parentheses, exponents, multiplication and division on equal ground just from left to right. Put parentheses around stuff if you want to group them together. Addition, subtraction, same thing, left to right. We're going to multiply real numbers and we're going to look at why a negative times a negative is a positive. Have you ever wondered why a negative times a negative is a positive? Are you curious? No curious people? Yes, one curious person. If there's one quality that I value above all others, at least in a student, it's curiosity. Maybe that might be the one thing I value above everything else in a person in general, but I haven't thought that hard about it. But definitely students, if you're curious, that's I like that a lot. So anyway, we're going to look at that. And the distributive property, I know that probably most of you feel like, yeah, got the distributive property, but here we're going to officially talk about it. We're going to prove it in a way and feel good about it. And I think what we're going to wind up with is some time at the end of class to get our assignments mostly done. Okay? How's that sound? Sounds like silence. Okay. It's early. It's early in the morning. So we're going to start in 1.2. It's the order of operations. I'll briefly re-explain my position. Maybe you were absent or something. And I'm going to just remind us of the same thing we did the other day. 38 divided by 2. Yeah, that was it. Okay. A little meme that swept across the internet for a while. So I'm going to assume that most of us were here the day we did this. But if you weren't, you need a reminder. What happened was I asked everybody to find this, to evaluate this expression. Put the numbers together in whatever way seems right to you and see what comes out. And you remember what two evaluations we came up with? There was 288 and there was 2. Now, that can't be. Like, we can't have one expression with numbers put together with certain operations be equal to 2 different things. So that's important. We can't have that. So what happens is it matters in what order you do each operation. That's why we call it the order of operations. Most people are going to add 9 and 3 first. So let's assume 99.9% of the population will do that. So here's where we diverge. Either you multiply these 2 together and get 24, or you divide these. You know what? I should move that over because that's on the right side. Or just cross it out. So either you multiply these together first, because that's just maybe how you feel like doing it, or maybe that's how you were actually taught to do it. Or you do 48 divided by 2 first and get 24 times 12. If you do it this way, you get 288. If you do it this way and you divide 48 by 24, you get 2. Okay. So then my question to you was what? What did I ask you when we discovered there's 2 different ways to do this? Which one what? Is right. Which one is right? And what did we decide? They're both right in their own way. They're right if in your universe, your reality, you're supposed to multiply numbers together first before you do any division, then you did it right. If in your universe you're supposed to divide numbers or divide and multiply from left to right, so if division comes first on the left, do that first. Then you did it right that way. But the thing is, we've got to agree that there's one way that we, at least as a class, are going to do it. So when I communicate to you, I want you to do a certain thing. I need to be able to rely on you to follow the same order of operations that I would follow. Okay? So the main disagreement comes with multiplication, division, and addition, subtraction. And the way we're going to do it is, well, parentheses first. I don't think there's any disagreement on that. Look in the parentheses and combine anything you can inside the parentheses. Put all that together. Okay. Then if you see any exponents, do that first. Here's an example of when you might have to choose between exponent and something else. Like 2 times 3 squared. Okay. Well, should I do the multiplication? There's clearly a multiplication. Or should I do the exponent to 3 first? Square first. Exponents, agreed. We all agree. Not because it's correct, but we just want to do it. Exponents first. Okay. If I want to do the multiplication first, I need to go above exponents to parentheses. Put parentheses around that whole thing, so that before you do exponents, we do parentheses. Okay? Parentheses are the almighty above everything else in the order of operations. Okay. Then multiplication and division. One is not taking precedence over the other. It's just top to bottom, and if these are on the same rung of the ladder, we do it just from left to right. Division comes first, do division first. If multiplication comes first, do multiplication first. Okay? So, which answer would we get if we followed this order of operations? And if we can finish it out for addition and subtraction. Would we get 288 or would we get 2? Nathan? We would get 288. Right? We did the division first. 48 divided by 2 is 24. 24 times 12, that comes next. 288. Okay? But I'll reiterate, I always also try to communicate things very clearly. If I want to do, if I wrote this, I would expect that you would do that. But if you got this, I would say, all right, maybe that's a little bit confusing. I'll be really clear. If I want you to get 2, what I would do is say 48 divided by 2 times 12, or 2 times 9 plus 3. I'll try to be very clear about that. That way, there's no confusion. There's only one thing you could possibly get because it made it that way for sure. But this order of operations makes it easier for us to write things in shorthand. Things like 2x plus 3. That's something that's a really common thing to write. Okay. If we don't agree on an order of operations, I've got to put parentheses out around every pair of numbers in order to tell you what I want you to do first. I want this 2 and this x to be paired together. You're probably used to by now, a 2 times an x be in one thing. It's grouped together. It is one number. You multiply those 2 numbers together to get that one number. But really, if we don't have an order of operations we agree upon, I would have to use parentheses to communicate that those are paired up like that. So, using an order of operations lets us shorten that down significantly. And there's lots of other instances where it shortens everything up. Okay. So, let's see. Let's do number 17. It's 3/4. So work that out in your own notes. Clean it out. first we're going to look at parentheses. We're going to work at any parentheses that we can, and if we have a large parentheses like this, really these are called brackets, square brackets, but the same thing as parentheses. Any kind of collecting apparatus like a parentheses, we're going to look inside of those first. Well, inside of these, we can call parentheses really, we have another parentheses. So to do these parentheses, we have to first start with these parentheses. And if there happen to be another set of parentheses inside there, we have to go inside. Right? So to evaluate any parentheses, we have to go to the furthest in set of parentheses. So here's the first set of parentheses. We just have to find that sum, 13 minus, that's 5. And now that the parentheses has been evaluated, no need for parentheses anymore. So now we square this. I saw this out there as a next step. Okay, what happened there? What did this person do, Cameron?
They multiplied 5 by 5.
Right? Why did they feel like they should do that?
Because the exponent.
Because there's an exponent there. 5 times 5 is 25. But what?
You have to do the parentheses first.
Gotta do the parentheses first, right? Do the parentheses first, then exponent. So back it up. Okay, so what should our next step look like? Yeah. 13 minus 5, which is 8 squared. All right. And so, what next? Should we multiply the 3/4 by the 8? Why not? Exponent comes before multiplication. All right, it's because we've agreed to do that. So 8 squared, that's 64. Whenever I multiply fractions together, I always at least mentally put one of them over 1. If it's a whole number, I put it over 1 just so I know. Now we could multiply these together and get 190, what, 192? 192 over 4. But then we'd have to ask ourselves, can 192 over 4 be simplified? It would be a little bit easier if we back up to here. Okay. Simplify. Can we cancel the 4 with a 3? No. 4 with a 64, yeah, Jamie?
4 goes into 64, 16.
So 4 goes into 64 16 times. So if we divide this by 4, we get 1. Divide this by 4, we get 16. That's a little nicer. 3 times 16 is what? 48. Seems ready. Okay. How's that? What do you think? People seem to do pretty well as I walked around. Any questions? Or disagreements? Okay. And if you disagreed, if you got a different answer, you'd have to justify it using this, our order of operations, the one that we have agreed that we would use. Mostly because that's how I was taught, and that's what the book does, and so that's how we do it. Well, then let's move on to multiplying numbers together. That takes us to 2.4. Jumping over to 2.4. So we know what multiplication is. We've been doing it a very long time. All right. Really, we boiled it down last time and the time before. Really, it all comes down to that there are numbers, right? Starting with 1. That's where it all began. And then adding 1 to 1 is the next step of math. Okay? So we can take numbers and we can add them together. That's really all we ever do. Okay? Multiplication is just a shorthand of doing addition over and over and over, right? Okay? So how can I represent 3 times 5 with addition? How can I rewrite this using this, write it out really long using addition? John?
5 plus 5 plus 5.
5 plus 5 plus 5. We could also look at it in another way. Cameron?
3 plus 3 plus 3 plus 3 plus 3.
Yeah. 5 threes or 3 fives. Either way, it all works the same. We add those together, we get 15. Add those together, we get 15. And there you go. So something about multiplication, or some properties about multiplication. There's the same properties about multiplication as there are about addition. So let's say that multiplication is commutative. A times b, any number times any other number, is equal to taking the second number and multiplying it by the first number. Pretty much what we did here. We can think of it as 3 times 5, and this is 5 times 3. 3 groups of 5, 5 groups of 3, it doesn't matter, you still get 15. Commutativity. And it's associative. Multiply a number times another number. Take that, multiply it by a third number. It would be the same as if you took the first number and multiplied it by the second and third multiplied together. Same thing. Okay. We also have things like the identity. The multiplicative identity is called the number 1. It's called the identity because 1 times a equals what? A. 1 times a. It's just a. Any number times 1 is just itself. The number that got multiplied by 1 maintained its identity. That's the identity element, is 1. Because you multiply by 1, nothing happens. Which is nice, because if we have a variable multiplied by a number, and we can somehow get that number to be 1 times our variable, that helps us to solve those equations. Shrink this a little bit. And then there's the multiplicative inverse. I can multiply a by 1 over a. What do I get when I multiply a by 1 over a? Wait on you for this one. A times 1 over a, that's just, you could write this as a over 1. A over 1 times 1 over a, that'd be a over a. What's a over a? It's 1. Huh? It's only 1. Only 1. Could be a, unless a is 1, which it's not necessarily 1. So a times its multiplicative inverse, 1 over a, is 1. So multiplied by its reciprocal, you get 1. So now let's talk about multiplying by negatives, because we know what multiplication is, we have so much practice with it. All right. First, let's multiply a positive times a negative. I think that one's pretty intuitive. Let's say 3 times negative 5. Could you use addition or maybe subtraction, something like that, to represent 3 times negative 5 in a way that you come out with negative 15? We know that's what you're supposed to get. But if 3 times 5 is 5 plus 5 plus 5, could we do this in such a way that we do that addition again, but we come out with negative 15? If this makes any sense, what I'm saying. What do you say, John? How would we represent this so that we come out with negative 15?
Okay, it'll probably be negative 5 times negative 5 times negative 5.
How about negative 5 plus negative 5? Plus negative 5?
Yeah.
So we add them. So in multiplication, we're just taking this number and we're adding it up this many times. So if we take this negative number and we add it up negative, add it up 3 times, we get negative 5, minus another 5, that's negative 10, minus another 5, that's negative 15. So we're out on negative 5 3 times. Now, that I think makes some sense. We can see that. Okay. But then if we do negative 3 times negative 5, what should we get when we multiply negative 3 times negative? 15. Okay? I'm not here to tell you that negative times negative is positive and end it and tell you something you already know. Okay? I want to show you, convince you that it has to be 15. Negative 3 times negative 5 is positive 15. Okay? We could use something like this, but then in that we would have to almost already accept that a negative times a negative is a positive. Like say subtract a negative the same as adding. It's almost like I used the proof to prove the proof. Or the solution. So let's do it this way. Here's why a negative times a negative is a positive. Because it has to be. A lot of times that's what happens in mathematics. There was a point in time when negative numbers did not even exist. There was a point in time when 0 didn't exist. There was a time in history when 1 was beyond the understanding of human beings. Okay? So at some point we came up with negative numbers. The idea of a negative number wasn't too hard to understand. You give me $2, so I owe you $2, right? So it's kind of like I have negative $2. Once I spend that money, I have negative $2 because I owe you $2. So negatives we understand, it's like debt. So that's fairly intuitive. But then it comes a day, one day somebody tries to multiply negative times a negative, and then we try to decide, what is this? And we discover it has to be 15. It has to be positive 15. If it isn't positive 15, all of the other rules that we had before that, multiplication and division and addition and subtraction, all break down. Okay? So let's prove that. So to show that this equals 15, let's just come right over here, we grab green, and we'll do this. Negative 3 times 5 minus 5, or 5 plus a negative 5. Now this isn't the same as that. So we're going to use it to show that that has to be the case. All right. Well, what does this have to be equal to? I clearly can see it has to be equal to. I did the order of operations. No.
Negative 3.
Negative 3. Well, what do we get here?
Oh, 0.
0. Caleb? 0. We do negative 3 times 0. This is 0. 5 minus 5 is 0. So this has to be 0. We already know that has to come out. But in the process, we're going to get negative 3 times negative 5, and it's going to have to be 15. Okay. So I'm going to approach this problem in a different way. I'm going to take negative 3 and distribute it. We know about distribution. Is it safe to assume we know about distribution in general? Okay, we're going to prove distribution in a minute. But at this early stage, all this stuff mixes together. So here we go. Negative 3 times positive 5. There you go, that's that first part. And then what's the second part? No. We don't know what negative 3 times negative 5 is yet, yeah?
Negative 3 times negative 5.
That's all we know. We know it's negative 3 times negative 5. Okay. Well, this is just a different way to write this. What is this equal to? It's equal to 0. We know that from the beginning. Okay. Well, we already talked about this. What would negative 3 times positive 5 be? Okay, negative 15. I'll just write it. Negative 15. Plus, let's just say something we don't quite know for sure yet. We're still proving this. Plus something has to be 0. We know it has to be 0, and we know this has to be negative 15 because we already talked about positive times negative, a fairly intuitive thing. What does this have to be? Yeah?
15.
Got to be positive 15. Negative 15 plus positive 15 is the only way to get 0. Okay, so what did negative 3 times negative 5 have to be? It's got to be positive 15. Got to be. No other way for that to work. Okay. So it's less of an intuition about what a negative times a negative is, but more of it just has to be that way. It's got to be come out to be a positive. Otherwise, this wouldn't be true. If we could work this out and somehow get this to be something other than 15, we'd get something other than 0, and then this wouldn't be true. Right? So now, does this convince you? Or are you like, okay, definitely there's no other way for that to be? Convinced? Who's convinced? Okay. Who's willing to raise their hands? The same people who are convinced. Okay. Let me shrink this down. This one. So I've convinced you that a negative times a negative is a positive, but here's the thing: I didn't really prove that a negative times a negative is a positive, and it's just a technical math thing that I can't let rest. Okay, so I can't just show you that negative 3 times negative 5 is 15, and then say that works for all negative numbers times any other negative number. So what I have to do is take two things like negative a times negative b, and I have to show that that has to be positive a times positive b. It's got to come out to be positive ab. Okay. So we do the same thing. Let's start with 3 could be a and the 5 could be b. So negative a times b plus negative b. Well, b minus b, also 0. This has to multiply together to be 0. Got to be that. So we distribute, and we get negative a times positive b plus negative a times negative b. We know that has to be 0. Okay. Well, here's negative ab, and negative times a times b, plus something equals 0. What does that thing have to be? We're going to cancel out this negative thing? Yep. It's got to be the positive, like the exact opposite. The exact opposite of negative AB would be positive AB. So negative A times negative B has got to be positive AB, because we know that this has to be AB. So any two negative numbers multiplied together give you positive. Now in the end, what have we gotten? That a negative times a negative is a positive. Right? So if you knew a negative times a negative was a positive, and you were operating that way, you're just fine. The only thing you gain from this is you can prove it. You can show that it's got to be that way. If you like that sort of thing, like I did going through school, great. If you don't care, you can still go about your life same as you always had, knowing that a negative times a negative is a positive. Okay? Anybody like that? Anybody like that? Who liked that? Oh, 3, 4 people. That's high. That's a high number. So I'm glad. What? You liked it? Did you like it? Or you're sleepy?
Yeah, I'm sleeping.
Okay. Thanks a lot. That's good. All right. So you know what multiplying numbers, how that goes. I've already seen from the work that you've already done. I'm confident that you'll do well here in this section. So we're going to go on to 2.5. Talk about another thing that I've seen a lot of you doing well, but now we're going to look at it and be sure that it works, and not that we're just throwing it out there. All right, so it's distribution. So the distributive property says a times b plus c equals what? What does that property say? What is that equal to? Cameron? No, not Cameron. Nathan.
A times B plus B times C.
A times b plus a times c. That's it. That's the distributive property. You want to distribute something, multiply it by the first thing, multiply it by the second thing, add it together. Keep in mind that negatives might be involved. Okay. So I'll show you a specific example. 2 times x plus 9. Well, if x were just some number, we would add the two numbers together, then we multiply the result by 2. That's what we've been doing. That's what we did in 1.2. We added the parentheses together and then multiplication. All right? But now we can't add them together inside the parentheses, that's not possible because they're not like terms. Okay? So if we want to manipulate this expression, which we will want to do very soon, we've got to break out of those parentheses in a way. We've got to in some way resolve these parentheses, and that's what distribution does. So this would be 2x plus 18. Confident that at least 95% of you get that. Okay. One way that we can represent multiplication graphically, so in a picture, is with area. Say I have a rectangle. This side's 3, this side's 5. How do I find the area of this rectangle? Is that? You're saying stuff over there. I see your mouth moving. Yes?
Wouldn't you add this 3?
Add what?
Add 3 and 5.
Is that the area? 3 plus 3 plus 5 plus 5? What's that? Oh, what is that when you add 3 and 3 and 5 and 5? The perimeter is the perimeter. That's, if you were to walk along this side, it would be, let's say, 3 steps, whatever. Let's say 3 feet. Okay? And walk along this side, 5 feet. If you were to walk all the way around the perimeter, you'd walk 3, 5, 3, and another 5. You just add all those together. You get the perimeter. Okay? You get 16. The area, though, if we mark off this side, right? 1, 2, 3. This side, 1, 2, 3, 4, 5. The area is a definition. It's not just something that has to be. It's something we decided we were interested in knowing. You know, like how big of an area is this? Area is measured in square units because we like to mark off these little squares and say how many of these squares would fit in here in this area. Okay. So how many 1 by 1 squares would fit in this rectangle? Yeah. 15. 3 times 5. There's, so this is 3 feet. Okay. So 1, 2, 3, let's say we have 3 rows. And then here we have, going this way, 5 feet across this way. So 3 rows of 5, 15. So 15, let's say these were feet. You got to establish some units. Feet squared, because when we multiply this lateral dimension by this lateral dimension, we get this square dimension. And just to take it a step further, we could maybe lay the square down on its side. Or let's say it's a rectangle. Say that's 3, that's 5. And then we make like a box on top of it. That's 7. Okay. We do 3 times 5 times 7. Well, here's that 3 by 5. Okay. And you multiply that by 7. What have you just found? The volume, right? Because this is 7. 1, 2, what did I pick an even number? 1, 2, or an odd number. 3, 4, 5, 6, 7. All the way across here. If we were to take that bottom piece here and extend it all the way up through all 7 feet of the height of this box, then what shapes would we get? Squares? What would we get? Yeah, John? Rectangles. Well,
Oh, cube.
we get cubes. Yeah, we get these 3-dimensional things that are the same measurement on all 3 sides because we're measuring them in feet, 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 and feet, feet, and feet. So we get all these cubes. That's why the unit of a volume is cubed. So we get 3 times 5 times 7. 3 times 5 times 7. 105? John's telling me yes. Feet cubed. I was double checking that. I got it right. Do that in my head. Okay. So 105 feet square, feet cubed. All right. So back to here. One way we can represent multiplication is by talking about area. 4 times 6 is just the area of this rectangle. The area of that would be clearly 24 feet squared, whatever the unit is. So we can represent it by multiplication. So here what we want to do is multiply 2 by x plus 9. 2 times x plus 9. And any multiplication can be represented by the first thing times the other thing. One is one side and the other is the other side. So here's 2. Okay. So that's that side. The other side of the rectangle needs to be how long? How long will this side of the rectangle be? In this example, 4 times 6. One side's 4, other side is 6. So here, this is 2. This side needs to be what? Cameron?
9.
It needs to be 9. Can we stop at 9? Say that's about 9. Will 9 cut it? Just 9? 9 and x more, right? If this were 3, if x were 3, then how long would this side be? 9. 12. It would be 12 long. If x were 4, it would be 13 long. If it were 11, it would be 20 long, right? It's that x more gets added on to it. So, well, let's just represent x with maybe a dotted line, because here's the problem with representing x as a line. That line is something. I can measure that line, right? You can't measure x. X is this, who knows? Who knows what it is? It is unknown at this point. So I made it a different color, I made it dotted to try and highlight the fact that it's this length that we can change. Whatever it is though, we're gonna add it to 9, and that's gonna be the length of that longer side. We all okay with that? That's all okay. Okay. So this side's 2. This side, this side right here is 9 plus x. Alright, so we will finish off the rest of the sides of this rectangle. So we know if we multiply 2 times 9 plus x, we'll get the area of this rectangle. Well, let's cut this down right there. Let's look at this as 2 different rectangles. What's the size of this rectangle? 18. 2 times 9 is 18. How long is this side? This side right here? It's 2, right? This 2, it's a rectangle, so if we go along and we measure from bottom to top, we should always get 2. So this side's also 2. Forget about that. So how big is the area of this rectangle? 2 times x. Whatever x is. If 2 is, or sorry, x is 3, 2 times 3 the area would be 6. If x was 7, 2 times 7, the area would be 14. Depending on whatever x is, the area will be 2 times that number x. So what's the area of the whole rectangle? This much plus this much, 2x plus 18. Or, if we wanted to show it in general, A, B, plus C. I'm just making these links up off the top of my head. Call this B, call this C, so this side is B plus C. This is AB, this is B, or A times C, so the area is AB plus AC. At the end of the day, we still have distribution, just like it's always been. But we get to see a little visual proof if you're a visual learner, if you like to be able to look at something and hold it. You can hold this rectangle in your hand, you can see the area, you can measure it off, and you can find that this is 18 square units here. You can find that this would have to be 2 times whatever this x distance is. You can see it, you can almost feel it, and it's more concrete that way. So what we get is just a concrete assurance that distribution works every time, because we can always represent it as a rectangle and find the area that way. Okay. Let's see. There's one that I like. If I can find it. Yeah. Let's do one together. the rest of the time, you can just work on your homework. You can get done and not have any tonight. So the instructions here are to simplify the expression, so, carry out any operations you can, collecting alike terms if they exist, and see what you wind up with. Okay, so I'm going to talk about a couple of things, a couple of mistakes that I'm seeing quite a few of. The first, most common, is doing this. Okay, 4a minus 1 is 3a. Okay, so it's a mistake. Can't do that. Why is it a mistake? What?
Because they're not like terms.
They're not like terms. What are like terms? How would you define a like term? Just throw up a bunch over here. Okay. Are there any like terms with 4x? Terms like 4x. Which ones? Negative 5x. What makes them the same? Same variable. And they have a variable, right? Are these like terms with the number 3? Number 3 and 4x, are they like terms?
No.
No, because this is a number times a variable, some unknown value, and this is just 3. It's always 3. You can think of this as 4. This is just x plus x plus x plus x, right? 4 times x. So there's 4 x's over here. There's negative 5 x's over here. We can combine those together and get a one negative x. A negative x. Okay. Any common terms, any like terms with 3? No, 3 is by itself. It's the only constant up here. How about 2n? Does that have any common like terms? 3n. Okay, how about 5n squared? Is that a like term? 6n squared, is that also a like term? Okay. Well, the only like term with 2n is 3n. They have the same variable. They also have the same, variables have the same what? The same power. N and n squared are totally different things. They're related, right? One is n, but the other one is n times itself. Okay? So this we could represent just 2 times n, 3 times n. There's 2 n's there, there's 3 n's there. Of course, these are like terms. We could just collect all of these n's together. There's 5 of them. Here we have n squared. N squared is n times n. Plus n times n plus n times n plus n times n, and here's the fifth one, n times n. Are n and n times n the same thing? Okay. They are similar and they can interact in certain ways, but can I add an n plus an n times an n? Think of it this way. Let's make n a number, a specific number, 5. 5 plus 5 times 5. Can you add those together? And you can add them together, but can you do them in a way where you can just say, like, 3 times 5? Is that 3 times 5? It's not that. It's not 3 times 5 squared. It's not 2 times 5. There's no way to put them together in a way that you could, over here, say, what, 3n squared? 2n squared? There's no way to put them together. It's like when we try to add two fractions that don't have the same denominator. They're just not the same thing. You just cannot get together two things that are unlike each other. Okay? Look at it this way. We could look at it as a picture. This length right here, from there to there, we call that n. All right. So if I want to represent n times n, we can do like we did before with multiplication or area. This side is n, this side is n, so here's n squared. You can see visually, is this thing the same as this thing? This is a square, and this is just a line. I can't add these two together and say that I have two of anything. Does that make sense? They're not the same thing. It's apples and oranges. Here we got apples, here we got oranges. Can't compare them, they're not alike. So, only like terms we have, I shouldn't have done that. Oh jeez, I'll just leave it. So, does 5n squared have any like terms? 6n squared. So 4x and negative 5x were like terms. Why? What do they have in common? What was alike between them? The what? The variables were the same. So if we were to write a rule for like terms, one, they have the same variable. But that's not enough. Because these are the same variable, right? But we discussed a few different ways how they're not like terms. They're not the same kind of thing. We can't add them together. So what else do they have to have alike? The power has to be the same. So the same variable with the same power. Then we can put them together. Right? N cubes can go with n cubes. X to the 7th can go with x to the 7th if you're adding them together. But you can't add x to the 6th plus x to the 8th. It just don't mesh. It doesn't make sense. They're not the same thing. It's apples and oranges. Okay. So that's the first thing. So can we, in the order of operations, can we put together the stuff in the parentheses, 4a minus 1? We unify them and make them one thing, and then multiply that thing by 2. We can multiply by 2, but we can't put them together. We can't unify them into a single term. Okay, so no, we can't do that. Gotta leave 4a minus 1 just separate. There's no way to unify them, no way to collect them together. Another common one I saw was this got left alone, and then this became 2 times a. What's wrong with that? If it's wrong, this must be different from that. Is this different from that? How are they different? Jada?
Well, the one has a different variable and you're also multiplying instead of adding.
That's what,
Yeah.
okay, so here you're doing what?
Multiplying instead of.
Yeah, when I write 2 and an a right next to it, I mean 2 times a. But 2 plus a is what I started with. 2 plus a and 2 times a, not the same thing. So we can't combine those together. Well, with those two pretty popular ideas out of the way, what do we do now? How do we simplify this at all? Yes?
Would you distribute 2?
Distribute the 2. You might have thought, I'm not going to distribute that 2 because that 2 is over here, it's not over there. Pretty common thing to do. Does it matter if the 2 is over here or if it's over there? No. I'm going to use a vocab word that we learned. Multiplication is commutative. It doesn't matter if I put a 2 over there or a 2 over here, it's going to be the same thing. So whether the 2 is here or there, I can still distribute it into the parentheses. I can distribute it this way. 2 times 4a, 8a. 2 times negative 1, negative 2. Okay? So that resolves the parentheses. The purpose of the parentheses is over. The purpose of the parentheses was to group them together so that they would get multiplied by 2. That's been done. They've been multiplied by 2. No need for the parentheses. Now we take the result and add a. And finally we have what? We have like terms, 8a and a, 9a minus 2. 9a minus 2. So this tells me we've got to highlight some stuff here. Okay, we've got to talk about this a little bit. So let me just kind of randomly throw some stuff up here. I want to use the same number. X minus 2 n plus 6 squared 3. Okay. First of all, let's talk about terms, because we've been talking about terms already. We've been talking about like terms and not like terms. Everything in here that's separated by addition or subtraction, we call a term. I'll try and color code this whole thing. So all of these, this guy, that one, this guy here, and there. Actually, I should really say this one here. Right, we're adding those together. This one right here, and this guy right here, we're adding those together. all of those in red are called terms. All called terms. And some of them are alike. Which ones are alike? 3x squared and 5x squared. Yes, like terms. So these are like terms. Okay. Any other like terms? No, we do have two ends, but they don't have the same power, as we talked about originally. You gotta have the same power. Okay, so this term is negative 2n, this term is 6n squared, this term is negative 3. Okay? Those terms over there, they have variables in them. This one, right here, because it doesn't have any variable, is called the constant term. It's constant. It doesn't change. If n changes or x changes, that's still negative 3. You can't affect that. So it's constant. It's the constant term. I'll do some orange here. Okay. So I just drew orange rectangles around all those things. What do all those things have in common? Jada? Just throw it out there. What do you think? Okay, they are all whole numbers. They do have, well, they're all integers, because this one's negative. So they're all integers, but that being true, that's trying to get at something else. But you're right, they're all integers. But this is an integer too, and it didn't get outlined in orange. So there's something else that these have, and it's not just that they're integers. And it's how
They all have variable values.
they're all paired up with a variable.
Yeah.
Yes, they're all multiplied by a variable. Not added to, not subtracted, but they're multiplied by a variable, and that's what makes them all coefficients. All coefficients. It's a funny word. It just means a number multiplied by a variable. And lastly, this guy right here. All right. Just underline these. We've already said what they are. We just said what they were. What are those things? They're all variables. They all vary. Until we set this up and put it in an equation, they're variables. They can change. They can be whatever we want them to be. Once we put them into an equation, now they have to do something specific. They have to be equal to 7 or 0 or something. So right now, they're free flying. Doesn't matter. They're variables. They vary. So when we are simplifying expressions, let's make sure we're only collecting like terms. We're not putting unlike terms together, and we're following the order of operations that we agreed on, our order of operations. Okay. Let's look at, still talking about like terms. Two x plus 3xy. How would I put these together? Add them together, 5 of something? 5.
Would it be 5x squared
Okay. What is x squared? What does it mean to say x squared? X times x. Okay. But we're trying to at least add two things together with x's, and that's addition, and then if we make it x squared, that's multiplication, right? So if we put two x's together with addition, it's not x squared, that would be 2x. Okay. But, I mean, I'm just kind of guessing at this point anyway, so it's a plenty fine guess. Any other ideas how we could possibly put these together? We have 5 of something, of some common thing. Who thinks these are alike and should be able to be put together somehow? Okay. Cool. 3 people. Who thinks they're not alike and you should just leave them alone? Okay. Got 5 people voting all together. It's about tied. 3 to 3. This large class. Well, they are not the same thing. They're not like terms. This is the number x. This is the number x times y. If x, let's just say for example, x is 3 and y is 5, this would be 2 times a 3. This would be 3 times a 15. Okay? This is 2 groups of 5. This is 3 groups of 15. They're not the same thing. They're not the same thing at all. So it's hard because they do both have x's, and both of those x's are both to the first power, but that y there makes it a completely different thing. Okay? So, the only thing we can possibly do is to say, hey, they both have x's in them. That's like I had something like this, and I distributed an x to both of them. We could do that. They have an x in common, a factor in common, and we can bring that outside of parentheses like we had distributed the x. But they're not like terms. We can't put them together. We can't add them together. All right. Any questions from anything today? Then we have 5 minutes, so I don't want to see you packing up your stuff. You got time to work on at least a few problems. You only need like 1 whole minute to pack up your stuff. Don't pack up your stuff. You got different paper for your homework. Okay. Let's get started. Let's do a few more problems at least. I'll come around, see how you're doing.